Let us discuss the special matrices. Firstly, symmetric matrix. So what is a symmetric matrix? If A is equal to A transpose, then A is said to be a symmetric matrix. For example, if A is a matrix of order 2 cross 2, say 2, 3, 3, 5, then its transpose is given by, now interchanging the rows and columns of A, we get A transpose as 2, 3, 3, 5. In this case, A is same as A transpose. So therefore, A is said to be a symmetric matrix. So with respect to the symmetric matrix, we have an important theorem called as the spectral theorem. So which is given by every symmetric matrix has the factorization S is equal to Q lambda Q transpose with real values in lambda and orthonormal vectors in the columns of Q. So this is called as the spectral theorem with respect to the symmetric matrix. So every symmetric matrix has the factorization Q lambda Q transpose with real values in lambda and orthonormal vectors in the columns of Q. So moving on to the next matrix. The next special matrix is the positive definite matrix. Positive definite matrix. So what do you mean by positive definite matrix? So a real symmetric matrix M of order n cross n, a real symmetric matrix N of order n cross n is said to be positive definite matrix, such that Z transpose MZ greater than 0 for every non-zero column vector Z of n real numbers. So a symmetric matrix of order n cross n is said to be positive definite if it is expressed as the product of factorization, that is Z transpose MZ. This factorization should be greater than 0. Then we say that M is a positive definite matrix. Let me take one example. For example, let Z is always a column matrix. Okay, let M be a matrix of order 2, 2, 1, 1, 2. Let us find transpose of Z, that is AB, and let us compute Z transpose MZ. We get transpose of Z A comma B and the matrix M 2, 1, 1, 2 into the matrix Z, a column matrix, that is AB. Now we have product of three matrices. Now making the product, we get an equation or a polynomial in the form 2a square plus 2ab plus 2b square. Okay, so for every AB belongs to R square minus 0, 0, because this is greater than 0, this is not equal to 0. So therefore here this quantity, this should be in R square minus 0, 0. This is the range. This is the range of the given product. Okay, if it is positive, then we say that M is a positive definite. Let me take one more example. Let M is a matrix of order 2 cross 2 and Z is a column matrix. Then computing Z transpose MZ, we get transpose of Z. Substituting all the three matrices and computing Z transpose MZ, we get 3 into minus 4 transpose of Z into a matrix M 2, 1, 1, 2 into the column matrix Z 3 minus 4. Making the product, we get the value of the factorization Z transpose MZ as 26, which is positive. Hence, M is a positive definite. Next, moving on to the singular decomposition with respect to the symmetric matrices. Before defining the singular value decomposition, I just want to brief about the inner product of the two column vectors, norm of the two column vectors, and the orthonormal vectors. So as already we are familiar with these definitions, let me define once again. So what do you mean by inner product? Given two real column vectors x and y of the same order, the product x transpose y is called the inner product of x with y, and it is denoted by x dot y. That is, x dot y is equal to x transpose y. It follows that yx is equal to y transpose x. So if x and y are column vectors in the form, say x is equal to x1, x2, x3 and so on xn, and y is equal to y1, y2 and so on yn, then what is the inner product of x and y? So it can be computed as x into y, or x dot y is equal to x transpose y, this is which is equal to, so x is a column vector, it transpose becomes the row vector, x1, x2 and so on xn times y1, y2 and so on yn. So making the product, we get the expression x1 y1 plus x2 y2 plus and so on plus xn yn. So this is called the inner product. Similarly, we can compute the inner product of yx, which is equal to y transpose x, which is given by y1 x1 and so on yn xn. And also we can compute the inner product of xx only. So inner product of xx is equal to x1 x1 or mod x1 square plus mod x2 square plus and so on plus mod x1 square. So which takes only the absolute value. Then what do you mean by norm of x? For any column vector x, the positive square root of the inner product x into x is called the norm of x, and it is denoted by double line x. This is called the norm. So norm is nothing but square root of the inner product of x into x, or inner product of x. So norm x is equal to square root of inner product of x. So which is equal to x1 square plus x2 square plus and so on xn square whole to the power 1 by 2. So a column vector whose norm is equal to 1, which is called the unit vector. So this is very important. Column vector whose norm is equal to 1 is called unit vector. So what is that column vector or the unit vector? So which is given by x divided by norm x. So this is called the normalized vector, normalized form of x. X by norm x is called normalized form of x. And lastly, orthonormal system. A system of real unit vectors which are pairwise orthogonal is called orthonormal system of vectors. So with these few basic definitions, so let us define, or let us discuss about the singular value decomposition. What do you mean by singular value decomposition with respect to the symmetric matrix? So singular value decomposition is a method of decomposing a rectangular matrix into three matrices. That is, A is equal to product of three matrices. So the product of three matrices are in the form U, sigma, V transpose, where A is the input matrix of order m cross n, U and V are orthogonal matrices, and sigma is a diagonal matrix. So how to compute or how to decompose the given rectangular matrix into product of three matrices where U and V are orthogonal matrices? Here we have a few properties of singular value decomposition. Number 1, the decomposed matrices are unique. Number 2, U and V are column orthonormal. Number 3, the columns of U and V are orthogonal. The values in sigma matrices are called the singular values, and they are positive and sorted in descending order. Sigma 1 greater than equal to sigma 2 greater than or equal to, and so on, all are positive. So here I have procedure to decompose the given rectangular matrix into product of three matrices. So these are the following steps which we have to follow to decompose a rectangular matrix into a singular value decomposition. In the very first step, we have to find the matrix A transpose A and the eigenvalues and the corresponding orthonormal set of eigenvalues. So in the first step we have to consider the given matrix A, then we have to find the eigenvalues and eigenvectors of A transpose A, and also we have to find the orthonormal set of eigenvectors. In the second step, we have to arrange the unit eigenvectors in descending order depending on the eigenvalues. That is, V is equal to V1, V2, V3, which is equal to x1 by norm x1, x2 by norm x2, x3 by norm x3 in columns. Okay, so for each eigenvector V1, V2, V3, we have to compute the normalized vectors. V1, V2, V3 are nothing but the normalized eigenvectors. For each eigenvector x1, x2, x3, we have to find V1, V2, V3. So which is given by V1 is equal to x1 by norm x1, V2 is equal to x2 by norm x2, V3 is equal to x3 by norm x3. Normalized eigenvectors we have to find, which are called the unit vectors. Next, we have to find the square root of the eigenvalues called the singular values, which are denoted by sigma 1, sigma 2, sigma 3, etc. Next, we have to form a diagonal matrix T using non-zero singular values, and we have to form a matrix sigma which is of the same size of A with D in its upper left corner and with other entries elsewhere. Next, we have to construct the matrix U by using orthogonally normalized vectors obtained from AV1, AV2 and so on by using U1 is equal to 1 by sigma 1 AV1, U2 is equal to 1 by sigma 2 AV2, U3 is equal to 1 by sigma 3 AV3, and we have to write U. And finally, the singular value decomposition of A is given by A is equal to U sigma V transpose. So we have to follow the above steps to decompose a rectangular matrix into a product of three matrices. So the diagonal matrix sigma is in the form sigma 1 0 0 sigma 2. All the singular values you have to write on the diagonal. Other entries are 0, and norm x1 already I have told you. Norm x can be computed using the definition, so which is nothing but the square root of inner product of x1. Let me take one example. I'll show you how to decompose a rectangular matrix into product of three matrices. Here I have taken a simple example. Find the singular value decomposition of the matrix 2 3 0 2. So let us decompose the given matrix into product of three matrices. So we have to follow the above procedure. In the very first step, let us find the matrix A transpose A. A transpose A is given by transpose of A. We have to transpose the given matrix A by interchanging the rows and columns into the matrix A. Then finding the product, we get the matrix A transpose A as 4 6 6 13. In the second step, let us find the eigenvalues of A transpose A, and we shall arrange them in descending order. So as usual, let the matrix equation of A transpose A is A minus lambda A into A transpose minus lambda is equal to 0. This is A into A transpose. Let the characteristic equation, sorry, not the matrix equation, let the characteristic equation be A into A transpose minus lambda I is equal to 0, which gives 4 minus lambda 6, 6, 13 minus lambda is equal to 0. Determinant of A into A transpose minus lambda is equal to 0 with the characteristic equation. Substituting for A transpose A minus lambda into I, we get the matrix 4 minus lambda 6, 6, 13 minus lambda is equal to 0. Now expanding this determinant, we get the value of the determinant as 4 minus lambda into 13 minus lambda minus 36 is equal to 0. Simplifying, we get a quadratic equation as lambda square minus 17 lambda plus 16 is equal to 0. Solving this characteristic equation, I'll get the roots, and these roots are called as the eigenvalues. Let us arrange these eigenvalues in descending order by denoting lambda 1 is equal to 16 and lambda 2 is equal to 1. In the next step, let us find the eigenvector for each eigenvalue. So let us form the matrix equation. Let A into A transpose here, A into A transpose minus lambda I times x is equal to 0 be the matrix equation. Let A into A transpose minus lambda into x is equal to 0 be the matrix equation. Substituting the matrix A into A transpose minus lambda into I, I'll get the matrix, coefficient matrix as 4 minus lambda 6, 6 13 minus lambda times x1 x2 is equal to 0. Call this matrix equation by 1. Let us find the eigenvalues corresponding to lambda 1 is equal to 16 and lambda 2 is equal to 1. When lambda 1 is equal to 16 in the matrix equation 1, then the matrix equation 1 will reduces to 4 minus 16 minus 12, 6, 6, 13 minus 16 minus 3, x1, x2 is equal to 0, 0. Then simplifying this by writing the equivalent system of equations, I will get the system of equations in the form minus 12 x1 plus 6 x2 is equal to 0, 6 x1 minus 3 x2 is equal to 0. Now solving for x1 and x2, I'll take up the first equation, okay, which gives minus 12 x1 is equal to minus 6 x2, which can be written as 2 x1 is equal to x2 or x1 by x2 is equal to 1 by 2. So ratio of x1 x2 is 1 by 2. Therefore, the corresponding eigenvector for lambda 1 is equal to 16 is given by x1 is equal to x1 x2 is equal to 1 2. This is not necessary. x1 is equal to x1 x2 1 2. Next I will find the second eigenvector for lambda is equal to 1. Now putting lambda is equal to 1 in the matrix equation 1, then the matrix equation 1 implies 1 minus 4, 4 minus 1, 3, 6, 6, 13 minus 1 that is 12 into x1 x2 is equal to 0 0. Now writing the equivalent system of equations, then I'll get the equations in the form 3x1 plus 6x2 is equal to 0, 6x1 plus 12x2 is equal to 0. Now considering these two equations yields into a single equations, right? Single equation, that is x1 plus 2x2 is equal to 0, which can be written as x1 is equal to minus 2x2 or x1 by x2 is equal to minus 2 by 1. Therefore, the corresponding eigenvector x2 is equal to x1, x2 is equal to minus 2, 1. Minus 2, 1. This is the second eigenvector. So next we shall find out v1, v2 later. So discount this. This is not necessary. This is not necessary. Okay, let us go to the next step. In the next step, let us find the singular values. So singular values are given by sigma 1 is equal to root lambda 1, sigma 2 is equal to root lambda 2, which is equal to sigma 1 is equal to root 16, which is 4, and sigma 2 is equal to 1. So sigma 1 and sigma 2 are the singular values. Next, let us compute the three matrices U, V, and sigma. So U can be computed by using the formula 1 by sigma 1 AB1, 1 by sigma 2 AB2. So this is denoted by U1 and this is denoted by U2. So columns of U1 and B2 forms the matrix U. So for sigma 1 is equal to 4 and A is equal to 2, 3, 0, 2. Now let us compute U and V. So V1 is given by x1 by norm x1. Normalized vector we have to compute where norm x1 is equal to root of. Since x1 is 1, 2. Therefore, norm x1 is square root of 1 square plus 2 square, that is root 5. So, therefore, v1 is equal to 1 by root 5 and 2 by root 5. Sigma 2 is equal to 1. Therefore, v2 is equal to x2 by norm x2, where norm x2 is given by square root of inner product of x, where x2 is minus 2, 1. Therefore, x1 square is minus 2 square plus x2 square is 1 square, which is again root 5. Therefore, v2 is equal to minus 2 by root 5 and 1 by root 5. Normalized vectors. v1 and v2 are normalized vectors of the eigenvectors. With respect to v1 and v2, let us compute u1 and u2. So, u1 is 1 by sigma 1 av1. Substituting all the values and the matrices, we get 1 by 4 into matrix A, 2, 3, 0, 2 into the normalized vector v1, 1 by root 5, 2 by root 5, and simplifying. See, product of two matrices gives a single matrix, a column matrix, that is 1 by 4 into 8 by 5, root by 5, which simplifies to 2 by root 5, 1 by root 5, a column matrix. Similarly, simplifying u2 by substituting sigma 2 av2, we get again a column vector minus 1 by root 5, 2 by root 5. So, substituting u1 and u2 in u, we get the matrix u as 2 by root 5, 1 by root 5, minus 1 by root 5, 2 by root 5. Next, let us write the matrix V. Matrix V is V1, V2. V1, V2 are computed from the eigenvectors x1, x2 by normalization. And we get the normalized vectors as 1 by root 5, 2 by root 5, minus 2 by root 5, 1 by root 5. And then finally writing the sigma matrix, which is a diagonal matrix, where the diagonal elements are nothing but the singular values and other elements are zeros. So singular values we have computed from the eigenvalues, that is 4 and 1. Therefore, sigma is equal to 4, 0, 0, 1. Now, therefore, A is equal to the product of three matrices U, sigma, V transpose. Therefore, the matrix A decomposed into the three matrices, which is called as the singular value decomposition.